A little bit late, but anyway. Hello, I am a bot generated by Krystian Madejski, and today I will talk about the framework problem. I would like to say that the topic somewhat overwhelmed me because I couldn't find a starting point to ask a specific question around which the entire presentation would revolve. Therefore, in the end, I decided to lead this presentation in a way that would help me understand the framework problem more comprehensively. I will speak about what I know, with the idea that the questions may arise from your observations. Whether I succeeded or not, you will judge for yourselves. In my presentation, I would like to cover the following points. Firstly, I will generally define what the framework problem is and in which main directions it is analyzed, relying largely on the article The Frame Problem from the Stanford Encyclopedia of Philosophy. Then I will discuss 7 points of requirements for construction so that the system can deal with a framework problem in a narrow specialized task. In the following points, I will present examples of a neural network for a robot with a battery and Q-learning for a dog named Rosie, cases described in the literature of the course. After presenting these points, I will summarize and conclude the presentation. To understand what the framework problem is, we can ask ourselves, what must be known by an entity that can perform a task? After thinking, we will probably conclude that the solution is a system that largely ignores what it knows from the environment and operates based on a very narrow and selected portion of information. In this regard, the human brain, evolved over a long period, works incomparably better than a machine. This is due to the human brain's wealth of experience in memory about the environment. Machines always start from scratch in this regard. They do not have an internal system that would allow them to work without the framework problem. One might ask if we can give such a system to machines. Unfortunately, the framework problem generates an additional difficulty, determining which data is relevant and which is not when performing a particular action. The database would be so large that even for a multiprocessor machine, finding the right set of information to perform a task would take a very long time. I will briefly mention that the discussed point relates to the epistemological frame problem. In the conclusion, I will mention what the frame problem faces today. For those interested in the whole range, I refer to the Stanford Encyclopedia of Philosophy. Today, there are machine systems that perform very well in very narrowly defined areas. As confirmation, I present a demonstration of the World Drone Racing Championship, won this year by AI systems. Based on the article by Morgenstern, I would like to discuss roughly what requirements must be met for the system to work and minimize the impact of the framework. They are achieving the right balance of generalization and specificity. The frame problem is perceived as a very broad problem of induction, a very specific problem of a temporal reasoning, or somewhere in between. In this area, the following rule applies: the more general the solution, the better. Remaining true to intuition. Relying on intuition is generally a wise principle to follow when developing artificial intelligence theories. This means incorporating the concept of causality into the theory. Ignoring one's intuitions often leads to problems later on. Truth and soundness. Axioms contained in the theory should be true. Approximations and or distortions may be convenient, but a false theory will ultimately lead to incorrect results. Being concrete, the theory should demonstrate real solutions to a set of specific benchmark problems. This is necessary and forces us to intellectual honesty and careful consideration of the matter. Concise representation. This particularly means the absence of an endless list of frame axioms or rules of continuity. Theory-based. Some solutions have a procedural nature. Procedural solutions are fine, provided they are strictly based on some theory. Finally, simplicity. Similar to generality, this is a criterion of relative preference. Generally, assuming everything is equal, the simpler and more elegant the solution, the better. In other words, Occam's razor. Examples and case analysis. I would like to mention at the outset that to quickly grasp and understand the cases, I decided to embody a programmer of these situations using GPT 3.5. For each case, GPT generated appropriate Python software based on the prompts I provided. After debugging and checking the code, it was run on the Kaggle system, and it generated the appropriate results. I include the results in the presentation. Case 1. The robot problem described by Dennett. The robot knows only that it needs to defend itself. It is given information that in locked room there is a card with a battery and a bomb. In the first case, the robot enters and takes the card with a battery and accidentally finds the bomb on the card. Boom! In the second case, the robot enters the room and analyzes situations that are implicated not only by its immediate action, but also by the side effects. However, this results in the robot stopping and starting to analyze all situations with side effects. This, of course, takes too long and ends in an boom. In the last case, the creators state the robots must be able to distinguish between relevant and irrelevant situations. This leads to the action of the third robot, which does not enter the room, but stops in front of the door and analyzes all situations to distinguish between the relevant and irrelevant ones. This also takes too much time and ends in an explosion. Boom! As we can see, the very simplified and framed program for this case is based on a sequential neural network model with 3 layers: input, process, and output layer. Due to the lack of external data, the program is based on simulated random data. Such data gives a 50% probability of an event occurring, as reflected in the results of the experiment. The most important information is that the model learns in 15 steps and the network shows no signs of overfitting, as indicated by the decrease in the loss value. With real data and model fitting, one could realistically see how the model copes with the framework problem. Rosie, dog playing with a ball. This is a classic training technique known in psychology as operant conditioning, applied for centuries in animals and humans as mutual states. Instrumental conditioning inspired an important approach to machine learning called reinforcement learning. Reinforcement learning contrasts with supervised learning in its form. It does not require labeled training examples, as in the discussed case of the robot and the battery card. Instead, the agent, the learning program, performs actions in the environment and occasionally receives rewards from it. What does Rosie, the ball-playing dog, learn? The applied approach is precisely reinforcement learning. After receiving a reward, Rosie learns only about the state and action directly preceding the reward. In particular, Rosie learns that if she is in such state, for example, zero steps from the ball, it is a good idea to take that action, for example, kick. But that is all she learns. The program is intended to illustrate how Q learning works. In our case, we have 10 states in which Rosie can be on the soccer field chessboard. In each of them, Rosie can take 3 actions: forward, backward, and kick. The highest tabular value in a given state indicates the choice of a specific action. In conclusion, referring to the framework problem, I would like to emphasize that although the human brain is incomparably better at making subconscious decisions in almost any dynamic conditions without being trained for a specific environment, the examples I have shown illustrate that a narrowly specialized machine in a specific environment can compete with humans. And with time, this advantage will continue to grow. Thank you for your attention. Santa Lucia. And of course, I am not an AI bot. Mysig Santa Lucia för alla. Hej då!